Today we're going to introduce some additional identities. In the last 2 days we did angle sum and difference identities for sine and cosine. Today we're going to take a look at the so-called double angle identities and half angle identities. Let's start by talking about the double angle identities. Here's what I'm talking about when I say double angle. Suppose we want a formula for sine of 2 theta. That's what we call a double angle. It's twice theta, hence double angle. You might hope or imagine or pray that this is just twice sine of theta. Unfortunately, it isn't. There's no such move allowed. You can't pull the two out or anything like that. It is a much more complicated formula. Well, it's not that complicated, but it's not as simple as this. So how do we find a formula for this expression, for sine 2 theta? The trick is to recognize that 2 theta is the same thing as theta plus theta. That's the big idea. So sine of 2 theta, then, is the same thing as sine of theta plus theta. Why is this useful? Because we now have the sine of one angle plus another angle. We have a formula for that. Let's remember what it is. In general, the sine of x plus y, where x and y are any angles, is sine of x times cosine of y plus cosine of x times sine of y. Now, that's true no matter what x and y are. So certainly it's true in the particular case that x and y are both the same angle, namely theta. So what we can conclude then is that the sine of theta plus theta, which as we just agreed is sine of 2 theta, the sine of theta plus theta is actually what? Well, it's this expression here, except with both x and y replaced with thetas. So that's sine of theta, cosine of theta, plus cosine of theta times sine of theta. Now, because x and y are both the same angle theta, these two terms, which ordinarily are different, are actually the same. If you look, those two terms are identical. It's just the order of the factors is switched. Sine, cosine, cosine, sine. So what we wind up with is actually 2 copies of that same term. 2 sine theta cosine theta. And that's the formula for sine 2 theta. So this is our final formula. Sine 2 theta is equal to 2 sine theta cosine theta. That's the so-called double angle formula for sine. Now, in class, I have you find this formula as well as the formulas, the double angle formulas for cosine and for tangent. But because you're watching this video, presumably you missed class or you already did it in class. So I'm going to quickly derive the other angles, or the other double angle formulas for you. So let's take a look at cosine 2 theta. So how could we find a formula for that? Well, once again, the trick is to say that cosine 2 theta is the same thing as cosine theta plus theta, right? And then we use the angle sum formula for cosine. So what would that be? That would be cosine of theta, cosine of theta. Usually it's just, the cosine of the first angle times the cosine of the second angle, but both angles are theta. And then minus, normally it's the sine of the first angle times the sine of the second angle. But again, both of these angles are the same. They're both theta in this case. So applying the angle sum formula for cosine, you get this, which of course can be simplified, right? Cosine theta times cosine theta is just cosine squared theta, minus sine theta times sine theta, that's just sine squared theta. So that is certainly a formula for cosine 2 theta. What's interesting is that for cosine 2 theta, there are actually 3 different ways of writing this expression. So this thing right here is one double angle formula for cosine, but because there are other ways of writing this expression, there are actually several different double angle formulas for cosine. So how do we get them? Well, one thing you can do is replace cosine squared theta with 1 minus sine squared theta. If I do that, I get 1 minus sine squared theta, that's what cosine squared theta is, and then minus sine squared theta. Well, that's easy to simplify. We just have two copies of the negative sine squared theta, so that's 1 minus 2 sine squared theta. And that is an alternative formula, a second formula for cosine 2 theta. So that's another double angle formula for cosine. And we can actually get a third formula by going back to this equation here and replacing sine squared theta with 1 minus cosine squared. So I'm going to copy this expression here, except replace sine squared with 1 minus cosine squared. So I have cosine squared theta minus, and now I need to replace sine squared with 1 minus cosine squared. I need to put the 1 minus cosine squared in parentheses because I'm subtracting this object, sine squared theta, and this object is this whole thing. So you need to be subtracting this whole thing, hence the parentheses. If you distribute the minus sign, you obtain cosine squared theta minus 1 plus cosine squared theta. And then we have two copies of cosine squared theta, so we can put them together to obtain 2 cosine squared theta minus 1. And that is the third double angle identity for cosine 2 theta. So we actually have three formulas for cosine 2 theta. Here's one, here's another, here's another. Now, you'll sort of ask yourself in applications, which one should I use? Like you're working a problem and you'll sort of wonder, which one should I be using? It depends. The answer is it just depends upon the information that you're given. This one usually isn't used. It's typically not very useful simply because it uses or requires or involves two different trig functions, right? That kind of sucks. This formula, though, only involves sine, and this formula only involves cosine. So depending upon the circumstances, if you have information about sine theta, for example, if an exercise tells you that sine theta is 3/4 or something, probably you should be using this formula because you know sine theta, so use the formula which only involves sine theta. On the other hand, if you know what cosine theta is, then use this formula because that's the formula which only involves cosine theta. On the other hand, this one requires both, so in many situations, in order to use it, you'd have to know both cosine theta and sine theta. It's usually not convenient to use. But it's good to know that all three versions of the formula exist. Now, let's consider tangent, right? We want a double angle formula for tangent. So tangent to theta, same trick as always. I can say, well, this is tangent of theta plus theta. And then I have to use the angle sum formula for tangent. Maybe I'll remind you what it is. So we derived it last time. The tangent of x plus y is tangent x plus tangent y over 1 minus tangent x times tangent y. So that's the formula I'm going to use, except both x and y are theta. So this thing here, the tangent to theta, is going to be what? It's going to be tan theta plus tan theta over 1 minus tan theta times tan theta. Great. Well, that can be simplified, right? In the numerator, we have tan theta plus tan theta. Well, that can be written as 2 tangent theta. And then in the bottom, we have 1 minus tan theta times tan theta. That's just tan squared theta. And that is the double angle formula for tangent. Don't be tricked. You might look at the 1 minus tan squared and think, oh, that's like a Pythagorean identity. I can replace it with something else. It actually isn't. 1 plus tangent squared theta is something, but 1 minus tangent squared is not a Pythagorean identity. So this is actually simplified. So that's the double angle formula for tangent. And again, you don't have to memorize these. They'll be given to you. But it is important that you know where they come from. You should, some of the identities we've derived have been a little crazy, but you should be able to derive these, right? You should be able to say that 2 theta is theta plus theta, and then apply the angle sum formula and simplify, okay? That's definitely something that you can handle. Well, okay, let's do maybe just like one or two examples using these new formulas we have. Suppose that I asked you to simplify the following expression. Maybe something like 2 sine, let's see, maybe something like 15 degrees cosine 15 degrees. Okay, now you're looking at this, you're probably saying, well, 15 degrees, that's not an angle on the unit circle. Now, there is one way of doing this without using any of the new identities that we discovered today. You could say, oh, sine 15, I can rewrite 15 as 60 minus 45, and then use the sine difference formula, and then do the same thing here, but use the cosine angle difference formula. Yeah, you could do that. It'd take a lot longer. What you should recognize is that this expression looks suspiciously like the double angle formula that we derived for sine. Here's the double angle formula for sine. Sine 2 theta is 2 sine theta cosine theta, right? Look at this. 2 sine 15 cosine 15. Very similar structure, right? So this is like other problems we've done before. The idea is that this expression is what you would obtain if you applied the sine double angle formula to something. The question is just, what's the something, right? So I claim that this is actually sine of twice something, right? And the question is really just, what's the something that goes here, right? Well, if you look at the formula for the double angle formula, notice that whatever angle appears here, theta, is the thing that appears here being multiplied by 2, right? So in our example, 15 is the angle that appears here, so it must be 2 times 15, okay? Now, if you think about it, it's easy to work backwards, right? If you took the sine double angle formula and applied it to this expression, you got sine 2 times 15, you would get exactly this expression, right? So it's kind of easy to go from here to here. That's like using the double angle formula in this direction, reading it from left to right. But really the key insight, the thing you need to do to solve this problem quickly is to recognize that you can use this identity in the other direction. If you have an expression that looks like this, then you can say, oh, that's actually just an application of the sine double angle formula, right? So if you ever wind up with anything like 2 sine blah, cosine blah, that is just an application of the sine double angle formula. You can this direction and say, oh, that's actually sine twice something. So this is, in fact, sine 2 times 15. And, well, that obviously is the same thing as sine of 30 degrees, which, of course, that's a unit circle value, so we know what it is, hopefully. It's a half, right? Okay? Because the angle is like this. It's like the smaller one. The y-coordinate is smaller than the x-coordinate, so the y-coordinate's 1/2. Yeah, so great. So be on the lookout for problems like that. A lot of the problems in this unit are of the form, we give you some expression that is simply what you would obtain if you applied one of these formulas. And the trick is to recognize that and then go backwards. Okay, so now I want to talk about the other class of identities that we've discussed, or that we discussed in class, and that is the half-angle formulas. Okay, so the half-angle formulas. All right, these are really great because they're going to allow us to evaluate, they're going to allow us to find the exact value of actually an infinite number of new angles, right? Like previously, we could only find the exact values of sine and cosine for angles on the unit circle. With the angle sum and difference identities, we were able to find sine and cosine and tangent of a few additional angles, like 15 degrees, right, because that's 60 minus 45, and 75 degrees because that's like 45 plus 30. These half-angle formulas will expand the list of angles for which we can find exact trigonometric values even further, and actually the number of additional angles for which we can find exact values is actually infinite, which is quite something. So here's the idea. What is a half-angle formula? What I want, basically, is a formula for sine of, like, x over 2. I don't know why I'm saying x. I could just as well say theta over 2. It doesn't matter the variable. So that's a half angle, right? I mean, x is some angle. We're cutting it in half, and we want to know what's the sine of x. Regrettably, it is not just 1/2 sine of x. There's no way to, like, pull the 1/2 out or anything like that. So that's wrong. There is a formula, but it's not as nice, okay? Now, in class, I give you a hint for how to derive these. Or actually, no, I do this full derivation in class. So let's do sine of x over 2, okay? And then maybe I'll just give you the other formulas because I don't want the video to go on and on and on. But let's do a full derivation of sine of x over 2, okay? So it's really not obvious the way that you're supposed to start. What you should begin with is you should start with the double angle identity for cosine, which we just derived a moment ago, right? Cosine 2 theta. Now there's actually, if you remember, 3 of these, right? There's 3 different formulas for cosine 2 theta. You should start with this one. So start with 1 minus 2 sine squared of theta, right? So that's one of the double angle formulas for cosine. Now, this formula is true no matter what theta is, okay? Whether theta is like a known angle, like 45 degrees, or 17 degrees, or an algebraic expression like x over 5 or something. This formula holds true no matter what theta is, which means that I can actually let theta equal whatever I want, plug that in for theta, and the resulting equation will be true. It doesn't matter what theta is. This is an identity. It's always true. So the trick is to let theta equal x over 2 in this equation, and then replace the thetas that you see here with x over 2's. All right? So here's what we obtain. We have cosine of 2 times theta, which theta is x over 2, equals 1 minus 2 sine squared of theta, well, theta is x over 2. Now, what you should notice is that the 2 times x over 2 simplifies to just cosine of x. And then we have this. Remember what I'm trying to do. I'm trying to find a formula for sine of x over 2. That was my goal. And sine of x over 2 is appearing right here. This equation just needs to be solved for sine of x over 2. If we can get sine of x over 2 by itself, we'll have a formula for sine of x over 2. So how do we do it? Well, start by subtracting 1. So I have cosine of x minus 1 equals negative 2 sine squared x over 2. Then we need to divide by negative 2. So that's cosine of x minus 1 over negative 2 is equal to sine squared of x over 2. The left-hand side can kind of be cleaned up. You know, if you take these two terms here, cosine x minus 1, and you switch their order, what that does is it induces a minus sign. Like this is the same thing as negative quantity 1 minus cosine x. That's what I'm saying there. Like if you distribute the minus sign, you get this, don't you? You get negative 1, okay, negative 1, and negative cosine, that's positive cosine, which is what I have here. So this numerator here, cosine x minus 1, is the same thing as negative quantity 1 minus cosine x. All right, over 2 equals sine squared of x over 2. And you know, you're probably wondering, why did I do that business with the minus 1 here? Because now this minus sign will cancel with that minus sign. And I can just write this as 1 minus cosine x over 2 equals sine squared of x over 2. If you're kind of, you know, strong with your algebra, maybe you can just jump directly from here to here. It's kind of a common move. If you have a minus b and you switch the order, that like produces a minus sign, essentially, as you can see here. So you can kind of think in your head, oh, if I switch these around, I get a minus sign, and that minus sign will cancel with this minus sign in the denominator, leaving me with this. Any way you want to think of it, that's where we are. We've almost solved for sine of x over 2. Of course, this is sine squared of x over 2. Remember what this means. This thing really means quantity sine of x over 2 all squared, right? That's what that notation means with the 2 here. So to isolate the sine of x over 2, I take the square root of both sides. So I get plus or minus, don't forget the plus or minus, 1 minus cosine x over 2 is equal to sine of x over 2. So that is the half-angle formula for sine. Now, I want to just take a moment to point out the fact that, yeah, we've got this plus or minus sign here, which occurred because we took the square root of both sides of an equation. What's the significance of the plus or minus sign? If you want to apply this formula, which one are you supposed to use? Are you supposed to use the plus or the minus? The answer is it depends upon the quadrant that you're in, right? Basically, you have to think carefully about, your angle x, right? You have to think about your angle x, and you have to think about, should my final answer actually be positive or negative? Okay, that's kind of the idea. Okay, so now in class I have you guys derive the half-angle formulas for cosine and tangent, but I'm just going to give them to you here. So the half-angle cosine formula is cosine x over 2 is plus or minus root 1 plus cosine x over 2. It's very similar to the sine half-angle formula. Okay, basically instead of a minus there, you've got a plus. And then finally, the tangent x over 2 formula. There's like 3 different versions of this. One is 1 minus cosine x over 1 plus cosine x. Turns out this can be rewritten as sine x over 1 plus cosine x. Basically, like if you sort of multiply top and bottom by the conjugate of the numerator, you'll get here. And this can be rewritten as 1 minus cosine x over sine of x by multiplying top and bottom by the conjugate of this denominator here. So these 3 expressions are all different versions of the half-angle formula for tangent. I don't really know which one is better than the other. I guess this one's kind of nice. And oh, there should be a plus or minus here. My bad. Let's be careful with that. I think that maybe this is better because it sort of doesn't have a plus or minus, and this one is also better because it doesn't have a plus or minus. But yeah, so 3 different formulas for tangent of x over 2. Well, okay, so let's do just one example to show you how we can use these things. So let's find cosine of 5 pi over 8. Okay, now that is a brand new angle. 5 pi over 8 is not in the unit circle, and it cannot be written as a sum or difference angles that are in the unit circle. So yeah, we really need one of these new formulas to find this thing. What you should notice about the denominator is that, the denominator is 8, and that's twice 4, isn't it? Right? So that's sort of telling you that, oh, this is a half angle. Like, this is half of some other angle. Well, yeah, I mean, it's cosine of 1/2 of what? Well, the 5 pi over 4, right? So 5 pi over 4 is a unit circle value. That's the idea. And so what I really have here is a half-angle formula. It's like 1/2 theta, right? X over 2, or 1/2 x. So essentially, here's my formula for cosine of x over 2. Basically, this thing right here, that's my x, right? So I've got cosine x over 2, in other words, cosine of 1/2 x. So I just use this formula, but replace the x with 5 pi over 4. So this is going to be equal to, let's see, plus or minus, so plus or minus square root of 1 plus cosine x, so that's 1 plus cosine 5 pi over 4 all over 2. Okay, great. And and I can evaluate the cosine 5 pi over 4. What is 5 pi over 4? Let me think about that. What quadrant is that in? Here's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. It's down there, right? So cosine 5 pi over 4 is negative root 2 over 2. So this is going to be 1 minus root 2 over 2 all over 2. Yeah, so we should simplify this expression inside the square root. So I have plus or minus, let's see if I can clean this up. I've got fractions within fractions. That's kind of bad news. Let's clean it up. So this is like 2 over 2, right? So combining that with this, you're going to have 2 minus root 2 over 2 all over 2, which is plus or minus root. We can keep it, change it, flip it now. You can imagine that this is like a 2 over 1. So we get 2 minus root 2 over 2 times the flip of this thing, which is 1/2, right? So that's plus or minus root 2 minus root 2 over 4. Okay, and I don't think that that can be simplified any further. Having a root within a root is kind of crazy, but these half-angle formulas often give you such things. However, we do have to address the plus or minus. It's either positive or negative, right? Like 5 pi over 8 is one angle, and the cosine of that angle is either positive or negative. To figure out which one, we just have to think about, like, where's 5 pi over 8? Right? Well, I mean, one way to think about it, we recognize that 5 pi over 8 is actually 1/2 of 5 pi over 4. And then we recognize that 5 pi over 4 is this angle right down here. So 5 pi over 8 has to be half of that, right? So this whole thing right here is, is 5 pi over 4. So where would half of that be? Would it be in the first quadrant? No, I don't think so. It would have to be, I think it's going to be somewhere in the second quadrant, right? It's definitely going to be bigger than pi over 2. So 5 pi over 8 is in the second quadrant, which means that the cosine of that angle should be negative, right? So I'm going to take the negative root 2 minus root 2 over 4, okay? All right, well, that was a bit of a long video, but there was a lot of material. And the good news is this is the end of the trigonometric identities that we will learn in this class. There are many, many more trigonometric identities out there, but this is typically as far as you'll go in a high school class. So, yeah, okay.